Hello everyone. In this video we are going to talk about creating shells, composite shells, and then beams in SolidWorks. So let's say you have this very thin plate and you want to do some static stress analysis on it, right? So here I created this solid model, this beam, where the dimensions are 40 by 200 mil and the thickness is 4 mil. So now if I want to do stress analysis on it, I go to simulation, go to new study, use the static analysis and get in. And when you analyze this object in SolidWorks, the SolidWorks FEA of course convert it into a bunch of smaller elements, right? And these elements are typically what we call tetrahedron, right? The 3D object, each face is a triangle, or could be a curved triangle, but that's what a tetrahedron is. If you want to see them, you can just right click on mesh and say create mesh, and then you should be able to see the shape of these elements, right? So you can here clearly see the shape of these tetrahedrons. Now, for many applications, you really do not need to have a 3D shape of the part and 3D mesh elements. It's just an overkill. It takes a lot more time and memory out of the problem. Now, for simple problem like this, it's no big deal whether you use 2D or 3D. But when the problem gets more complicated, it does matter whether you basically consider the problem to be 3D, which is using solid tetrahedron elements, or you just consider it 2D. Because let's say here, if you move along the y-axis, nothing would change. Let's say here I put a fixed support on the back plate and I put some load on the front plate, right, and make it a cantilever beam. So really going up and down, moving in the height direction is not going to add much to the analysis. And that's where you can convert the problem into 2D by using shells. So shells are 2D elements basically. They look 3D, but they have zero thickness. Or if in addition to the y that does not change anything, the direction for z also, which is the depth, does not change anything, then you might bring the problem further down and make it only 1D along x, and that is what we call a beam. So beam is converting the 3D object into 1D basically. So depending on the importance of you have 3D analysis or 2D or 1D, you can use solid models, shells, or beams, and that brings down the amount of calculations, memory, and everything. And if your problem really qualifies for such thing, the numbers that you get from 2D and 3D are going to be quite similar. So let me show you that here. So what I will do is I'm going to first do a 3D, right? So I go and create a fixed geometry here on the back plate, on the back of the plate, and then here I go and apply a load here on the front of this member. So here I use it downward, negative y direction, and let's say 40 or 50 newtons, right? And now I already meshed it, so as long as the material is defined, make sure your material is defined here. So let me apply some material, let's say stainless steel or something, for example. As long as the material is there, the geometry is there, the boundary condition and the loading, you should be able to run. And we're going to see the distribution of the stress, the deformation and everything, right? So this is how the stress is going to be distributed in 3D. And you see the level of stress is below the yield strength, so we are still within the elastic region, and the small displacement assumption is valid, so we are good, especially for stainless steel. right? And these are the numbers, and this is, as I said, the distribution of the stress and so on. Now, another way to handle it is to, as I said, convert it into shells, which are like 2D elements, and then compare. So here I go to model and I start a new static analysis. And this time I convert this 3D object into 2D shells. How? I right click on this plate and I say basically define shell by selected faces. It says, okay, where do you want it? And I say on this face. It says fine. Now it says how thick do you want it to be? And I say 4 mil. Use the same thickness as last one. Now as you can see, the plate of the shell is not coincident with the top surface because the offset is not right. So you have to go down and click on the offset option and then make sure it falls either below or above or in the center, right? So here, this is what we have to do, correct? And once we do that, you see now the shell does match the boundary of the part. And once that's the case, now if you see here now it is converted into shells instead of the solid object. Now if I right click and say or let me first mesh it and show you the mesh. So let me say create mesh, and I create some mesh, and now look. If you look now, this is a shell, this is the mesh element for the shell, and if you look at it from any direction, it has what? It has 0 thickness. And the mesh elements here are triangles instead of tetrahedrons, right? So now I am taking advantage of the simple geometry of this problem and I'm solving it as a 2D problem instead of 3D, using shells instead of tetrahedrons. And now if I want, I can go back and apply my fixture and everything, right? The load. So I right click here on the fixture, go to fixed geometry again, and I apply the fixed condition or the cantilever. The only thing is you should not really apply it on this part here, because when it's a shell, really what you can what SolidWorks understands from you is the top layer of the shell. So if I go back and show the mesh, really if you want to apply a fixture, you have to apply it on this edge, which is a part of that top shell. Do not apply it on the surface this time, because that surface does not exist anymore in terms of the meshing. Only SolidWorks considers the top layer. So here we go. Now that side is fixed, and now the same thing for applying the load. Again, I'm not going to apply it to this surface, I'm going to apply it to the edge, because again that top shell only exists in terms of meshing. So now let me apply downwards, and so I choose this direction here, and here let's say I want again the same amount of force, 50 Newton, right? So now you have something very similar, right? And again, you have to make sure your material is the same. So I apply again stainless steel, and now everything should be similar. So I run it, and there we go. So now if you look at this static 1 and static 2, you should be able to see, if you look at the numbers, 9.57 10 to the 7, and then here again look about 9.1 10 to the 7. So they are not going to be exactly the same, but very similar, and especially the distribution of the stress. If you look at these colors, you see they are very similar. You can use compare results and compare the results from the let's say all studies here, and I want to, let's say, look at the stress from static 1 and from static 2. And when you do that, it should bring both of them side by side. And now if you look, you see a huge degree of similarity and quite similar numbers, not exactly the same, but very similar. So anytime you simplify, you're going to lose a little bit of accuracy. You're not going to get the perfect equal thing, but you clearly see going from 3D to 2D, right, made some very similar results. So this is using a shell instead of 3D elements, okay? So this is the first thing. I have a solid model. I converted it into shell manually by saying create shell from specific faces. And I did that, and I could simplify my calculations. Now, before I move any forward to the composite and so on, let me show you other ways that you can create a shell. Because converting it from solid model is not the only way to create a shell. If you started with a surface instead of a solid model, you could still convert that surface into a shell, or if you started with the sheet metal, you could also again convert it into shell. Okay, so surface and solid and sheet metal can also be converted into shell. So let me show you those, and then we go to how to make that shell composite. So here we are going to make the same surface, right? So we choose the top plane, go to sketch and create the same surface, but in the surface design this time. And so we go to surface and then we fill it and we create this surface. So now there's a surface with 0 thickness, which is kind of like a shell itself. So now if I take this surface to a new static analysis, you see when you bring it in, it kind of comes in as like a shell to some extent, because it is a surface, but still it tries to say, hey, tetrahedron. But now if you right click here and say what? Edit definition, then now you can have what? You can define it as a shell, whether thin or thick. So let's say I want a thick shell and I want it to be 4 mils, and boom, look. So now it has converted it really this time to a shell, and if you go ahead and create mesh, you should definitely see shell elements, as you can see here. You're not going to see tetrahedrons. Okay, so this is if you want to what? Create basically shell out of a surface. Right click, say edit definition, and then define it as a shell. That's one thing you can do. The other thing is sometimes you have a sheet metal, right? So let's say you have this surface and then you go and convert this guy to a sheet metal, let's say with 4 mil thickness, like that, and now it is really a sheet metal, right? You can create bends on it or anything, or you can import it from somebody else's work. So now that you got your sheet metal, can I also convert this into a shell in the simulation? Sure. So this is a sheet metal. I go here to new study and again static. And now if you look at this part 3, here you see it has basically a surface and the solid body. What we really need is this solid model. The surface, we can right click on it and exclude it from the analysis, okay, because we don't need to do anything with that surface. So we exclude it, so we are only down to that solid body sheet metal. If you right click here, again, we can do what? We can say edit definition, and then we can again create what? A shell for it, and the thickness of it comes from the thickness of the sheet metal. So now this guy will be meshed as shell, right? Again, let's take a look here. I used edit definition, and then I say create a mesh, and then I create a mesh, and look again. You see, this is again that 0 thickness shell. So you can create a shell either manually or by edit definition. Manually from solid models, and by edit definition through surface and sheet metal. So this is how to create a shell. Now let's talk about some other things here. So let me close this for a moment and just come down to the solid model I have. So this was just creating a shell and analyzing as a shell. But one of the good things you can do with shells is you can create composites. Okay, composites, yes. So you can have basically different plies, different layers, and in each ply you have your main basically filament, right? Could be from any different material, from carbon fiber or anything else, that are kept together in the resin or any material that is acting like a glue, holding them, bonding them together in a layer. And you can have several different layers of composite material where these filaments are going to be at different angles. So you can create composite material for static analysis. How? So here, if you remember, this is the solid model. And remember how I made it into a shell, right? I right-clicked, I used the selected face, I clicked here, and now you can see not only I have thin and thick, I also have what? Composites. So I say I want a composite shell. So it's fine. How do you want to define it? I say, well, first of all, I want all of the layers or plies to have the same material. And I want it to have, let's say, 4 layers. And then you can either make it symmetric or sandwich or any format that you want. You can change your reference, right? So your reference right now looks like this, and the angles are measured from that reference. When here you go down to each layer and define its thickness and angle, that angle is measured from the reference that you can see. If that reference is not what you want, you can rotate it. So say, well, 4 layers looks good to me, and so here I go ahead and click on each one of these numbers. Let's say I make each layer 1 mil. The layers do not need to have the same thickness, and you can give each one of them a specific angle. So let's say the first one is 0 angle, the next one is like 30-degree angle, the next one is like 45-degree angle, and the next one is maybe negative 45-degree angle. Good. So the other thing is here you need to use the offset and make sure that your offset is right. So let me bring it down here. Correct. So I define it as composite. If you want to see it again, let me go back again and show you. So this is the composite that you made. And now each layer, when you click on it, you can see that the orientation of the filaments are different. So positive 45, negative 45, 30, 0, and so on. Each one has a specific thickness that you defined. And before you close this shell definition, you must remember to apply material. So here we said all the same material, but we have not specified which material. So you go here and you choose the material, or you can not check this and select different material for different layers. So here, to make it simpler, I choose the same material for all plies or layers, and then let's say I go to plastics and I choose, let's say, ABS, PC-ABS here. And this material, PC-ABS here, is linear isotropic, right? Which means linear elastic isotropic, means the material behavior is linear, elastic, and the properties of the material are the same in any direction, isotropic. For many of these composites, you have to use what we call linear elastic orthotropic. Okay, so they have different properties along different directions. Like if you see, for linear elastic, I only have 1 Young modulus, 1 Poisson's ratio, and so on. But if I change it to orthotropic, now you see along X, Y, and Z, or in the XY plane, YZ plane, and XY, XZ plane, I have to specify what? Different values for Poisson ratio and Young modulus, and then for shear modulus. Okay, so it depends. As I said, you have to really specify your material properly. But here I just try to show you the basics, so I'm not going to go into linear orthotropic, but pay attention. For many of these composites, you have to choose orthotropic. Okay, so here I just keep it simple. I say linear elastic isotropic, apply, close. And now I have everything specified for these layers. So now I should be good to go for running my simulation. And there we go. So now I got my stress, displacement, and strain on the whole part. Now, one good thing about the composites is you can see the stress or the strain displacement for each layer separately. You clearly see here I have ply number 1. So what you see here is only for the first layer. But I can definitely go ahead and change that, right? So if I go to this stress and go to definition, then for, as I said, composites, you see options. I can either choose to say maximum across all plies or uncheck it and say, well, instead of ply number 1, go to ply or layer number 2, right? So I say 2 and then I look at these numbers, right? See 5.19, 10 to the 7 and look at the stress distribution. Now when I go to layer 2, look, right? So I say 2 and I go to layer 2, there we go. The stress distribution is completely different, the numbers are completely different, and I can, as I said, change this, right, to other layers. So this is layer 3, then I can go layer 4. So that's one of the advantages of, or not additions, options for a composite. And you can also see that the strain has a similar thing, right? In strain, you can also have different layers, but not the displacement. The displacement cannot be discontinuous. So here you see clearly big changes when I go from one ply or one layer to another, because the stress and the strain can be disjoint, can be discontinuous in a composite material, but not the displacements, because if they are, then it means the layers will separate from each other. So the displacement does not have that option because it cannot be discontinuous. And one other thing could be about the safety factor. So if I go and say, hey, give me the safety factor, now you have different safety factor for composites. For regular material, if I go back here and show you for the material that are not composites, if I go here and say factor of safety, then it could be based on what? Maximum 1 mises of stress, which is for ductile material, or the Tresca, which is similar, or maximum normal stress, which is for brittle material, and so on. So these are the methods for determining the factor of safety, right, for a standard material without composites. But for a composite material, then the safety factor and the definition of that is different, right? So the methods is going to be like the Psi-Hill criterion, Psi-Wu criterion, max stress criterion, and so on. Okay, and I'm not going to get into any of these and explaining them for you because that's beyond the scope of this lecture. Last thing I want to mention is the beam. And I told you beam is like a 1D model. When here in the depth and in the height, nothing changes majorly, then you can only consider the longitudinal direction and only consider the 1D definition of the problem instead of 3D, and that's what we call a beam, and look at the stress distribution within the beam. Of course, again, when you're losing one dimension, your results are not going to be as accurate as 3D because you're doing simplification, but if that simplification and the change in the result is not really a big thing, and your assumptions of converting 3D to 1D is relatively fair and accurate, then that brings down a lot of computation and memory usage, and it's going to accelerate the process. So here I have this plate again, and I'm going to go to steady and go to static here. And when I right click, instead of tetrahedron or creating a shell, then I say what? Treat it as a beam. Okay, so if I say treat it as a beam, Then you see it adds two elements here at the two ends in the X direction. And now I can go ahead and create fixtures. So I go to fixed geometry, and you can apply your fixed geometry on basically a joint here. And for my joint, I choose this joint here. And it is going to apply your kind of cantilever connection or fixed connection over there. Then I do a similar thing to the load. So I have external force, can apply to a specific vertex or object or a joint. So here I choose a joint, and again I choose this front joint. And then you need to specify a specific direction. So I choose this direction here. And for magnitude of force, I use, let's say, 50 Newton, the same thing that we did before. You see it's downward, and now I have applied my force. And for mesh, let me show you how the mesh looks like. There we go. So you see the mesh is definitely 1D, okay? It is just made of, in this case, really a bunch of cylindrical elements that are just 1D. So make sure your object has the material, and then you should be good to go. So here I apply stainless steel and run, and there we go. If you remember, for the 3D object, the maximum stress was 9.57. For the shell, it was 9.1. And here for the beam, it's 9.375. So it seems like in terms of maximum stress, actually the beam is giving me a little bit better answer, closer to 3D than the shell does. Now, it's not always the case, but again, you see that the stress distribution, the fact that you go from smallest to the max, that is kind of similar to what you had in 3D and 2D, and the behavior, the overall behavior is correct, but this considered and used a lot less number of nodes, number of elements, and the calculations here are much simpler, although still relatively accurate. So hopefully this video was useful to you, and you learned how to basically treat a simple static analysis problem in either 3D or 2D using shells. Make shells composite if you want, and using beams. So thank you so much for your attention. I will see you in my next video.